Okay, so,
No, because vertical, we're lost.
I'll try to unlost you. How about that?
Find us.
Okay, so let's start with the hanging sign lab problem. Okay? And here's your overriding thing, is that you're gonna have two dimensions. You're gonna have the forces in the x direction, which have to add up to equal to 0, and you're gonna have the sum of the forces in the y direction, which also have to add up to equal to 0. Not pi, not the square root of 131.7, okay? 0. That's it, because the system's in equilibrium. So, when you look at these, for example, let's start with the data that you guys have. So, you took the scales and you hung a 9.8 Newton force straight down. So that first diagram that I want, okay, you're going to have it drawn to scale. As big as they are, you could probably just let 1 centimeter equal Newton. And so here's the point, is that you have the tension in the string going like this, and then you're going to have your force in the y direction, force in the x direction, this force in the x direction, that force in the y direction, and then a negative 9.8 Newton force acting down. Ideally, these two y components, when you add them together, are going to equal negative 9.8. In an ideal world, these two x components should be equal and opposite values. I cannot emphasize this enough. Everybody's data is different. All the angles are different. All the tensions in the strings are different. So the only thing I can grade you on are the calculations that you show. I don't have an answer key. I can only grade you on the work that you do. Okay? Now, when you get done with this diagram, it should look like a couple of triangles. Like this. That's what it should look like when you get done with that first diagram. To scale, you've measured the angles, not a sketch, drawn to scale. You don't have to draw it with the second one, only draw it with the first one. Okay. On number 6. So let's talk about number 6 on the back side. And this all hinges, again, on the idea that the forces are going to be in equilibrium. So here's what you've got. You've got a 30-degree angle here, and then you got a 20 Newton force here, and then you've got another scale over here, and this is what you don't know. But you do know that you're lifting up a 30 Newton weight. So here's the basic idea. Personally, are you out?
Yep.
Okay. Well, you don't have any homework, but they're going to start working on this lab. Watch the video. I'm going to post it on YouTube. Tell Scooter Mew to do the same thing. Not that she will, but we can say we tried. Okay. What I would do personally is that I would work off of this 60-degree angle out here. You don't have to. I like to work off of that 60 because it's easier to see those components that are on the outside. So, Luke, I got a 20 Newton force, which is the hypotenuse. I'm going to work off of this 60-degree angle. How can I find this x component? Sine, cosine, tangent.
Didn't you use the x cos? No, wait.
Yes. Because you know the hypotenuse, you know the angle, and you're trying to find the side adjacent to the angle. Cosine.
Yes.
Yes. So you can take the cosine of 60 times 20, that's going to get you some x value. Which in this case, hypothetically, might be 10 newtons. Maybe yes, maybe no. I'm just saying, okay? Let's say it's 10 for the sake of argument. So here's the story. So if you're going to make this negative 10 newtons, by default, what does your x component on the other side have to equal? 10, because there's no other forces. This is like the horizontal motion with the limb. If there's no other forces, and you only have two forces, the only way they can balance out is if they're equal and opposite. Okay? So as soon as I know what this value is in the x direction, I automatically know what the other one is. Okay? Got that one. Now, imagine this. Vertically, everything has to add up to 30. So if I can find this vertical component, let's say that's 18 newtons. Luke, what am I going to use? Sine, cosine to find that vertical side over there. Sine. Sine is 60 times 20, boom, let's say that's 18. So it's like this. I owe the bank $30. If I pay off 18 of it, how much of it is left? 12. So these two vertical components, y1 plus y2, have to add up to 30. So as soon as you know what one vertical component is, and you know what the weight is, subtract that from 30, there's your other side. So now you have two sides of the triangle. You have the x component and the y component. The reading on the scale is the hypotenuse. So, Chuck, how am I going to find the hypotenuse using my x and y components?
A squared plus b squared equals c squared.
Yeah, the Pythagorean theorem. Then, now you have to be careful. If you're going to work off of this outside angle and you're going to use inverse tangent and find this angle, keep in mind the angle that I want is that interior angle. So if all goes well on number 6, the reading on the scale should be something around your age. Okay? That's an ish, something around your age. And the angle should be around 40. Connor S., you like that?
Yeah, I like that.
Okay.
Pause.
All right. Now, let's talk about number 7. It weighs 8,000 newtons, which is a chunk. So, let's say you get to this problem and you think, God, I don't know what to do. Well, think this through. What if you were only lifting this thing with one cable? If you only had one cable, how much force would be on that one cable?
The full.
Full 8,000, right? So if you only had one cable, that would be 8,000, right? Now, instead of the angles, what if we had two cables that were lifting vertically? How much would be on each cable? 4,000 newtons, right? So do you agree that the two, no matter what, the vertical components each have to be 4,000?
Yeah.
That's what has to lift it. The vertical component has to be the 4,000. Now, this is where the geometry kicks in. So in the write-up, you have two different ropes. And I tell you that the angle between the I-beam and the cables is 70 degrees. So this is your 70-degree angle right there, because that's the angle between the ropes and the I-beam. Okay? That's 70 degrees. Again, if it were me, I wouldn't work off the 70. I'm going to work off this 20-degree angle out here. You can work off the 70. I'd like to work off the 20. You're going to get the same answer. So here's the story. The 4,000 newtons is the vertical component of that force. Okay, that's the 4,000 newtons. What are you trying to find? In effect, the what? I have no idea. You're trying to find the hypotenuse. So think this through. One side of the triangle was 4,000 newtons. You're trying to find the hypotenuse. What does your answer have to be bigger than? 4,000. Okay? If it's not bigger than 4,000, you have violated both Euclidean and non-Euclidean geometry, and that's pretty cool. Okay? And it's wrong, too. So, your answer has to be more than 4,000. Not a lot, but a little, okay?
You just want the tension of one, right? You don't
Yeah.
want the tension of both.
No,
Okay.
I just want the tension in one.
You just have to.
Chuck, that is a one white coat with the sleeves.
I look, you like that.
It's like, I look over, it's just like blinding. What?
And that third is in fact a leather jacket.
Okay. All right, now let's talk about number 8. So number 8, you've got this pulley system, and this is what I showed you yesterday with the demo. So, you got a 15 Newton force over here. You got a 31 Newton force over here. This is 45 degrees, and this is 20 degrees. So here's the main idea about this. To put this system in equilibrium, there's 2 ways that I can determine the tension on this rope. One is I take a Newton scale. That's what you did in the lab. You took a Newton scale and you hooked it up and you measured how much force was exerted on the string. Okay, that's what you did. It's an option. The other option is that you take that string, you loop it over a pulley so that it can find its own equilibrium, and then you begin to hang weights on there. Now, here's what you have to understand with strings and weights. If this is a 31 Newton force, which it is, that means the tension right here is 31 Newtons, which means the tension over here is going to be 31 Newtons. So I can either hook up a Newton scale and have the Newton scale read 31 Newtons, or I can hang a 31 Newtons weight on the end of it and generate 31 Newtons of force that way. Mother Nature doesn't care how you generate the force. Put in a Newton scale, hang weight, doesn't make any difference. But here's, mathematically, here's where this is important. So, pulling up this way, that's 31 Newtons. Going this way, that's going to be 15 Newtons. So once you realize this, number 8 is just like number 6. Okay? It is. It's the exact same process. Make your y components add up to equal to 0. Make your x components add up to equal to 0. That's all you have to do. Okay? So, but pay attention to what I want on those bottom lines where I say, here's your x components and here's your y components. I tell you, in big bold letters, I wrote prove. Prove that the system is in equilibrium by showing that the sum of the forces in the x and y direction are equal to 0. So what I want to see on that x component line is something plus something equaling 0. On the y component, I want to see something plus something plus something equals 0. So your x component should have two values that you're adding together. Your y component should have 3 values that you're adding together. Okay? We're good.
What is the weight around?
Around the angle on number 6.
Would that be positive or negative?
Now, that's just the absolute value. It's however you want to define it. The absolute value of the weight on number 8 is close to the angle on number 6.
Does it matter?
No. I don't care how you define it.
Okay.
I typically make the down values be negative.
Do we have to have that on? That same. I don't know what I'm trying to say. Does it have to be the same on the like y component? How we define it in
Okay,
weight?
let me put it this way, Chuck.
Come on, Chuck.
You're going to make your 3 y components add up equal to 0.
Yeah.
Can they all be positive?
No. No, I'm just saying. If I if I have it one way for weight and I have it another way for y component.
Why don't you just write the negative sign and make them the same?
I don't know.
I don't care, as long as you define them as being positive and negative. I don't care which one is which.
I mean like the same answer. Okay. I'll let it go.
Chuck, I don't even know what you're asking, man.
The weight is positive for my weight, but it's negative for my y component.
That's fine. As long as they add up to equal to 0, that's all that matters. Okay.
Yeah, so I didn't need the negative sign, Asher.
Or you should
Get that out of
make it easier, not waste 5.
But you gotta make something negative. I think that's with Thatcher's point.
No, he has it negative in his y component sum, like for his proof.
Yeah.
And he has it positive on the weight little line.
That
They
just
need to
feels
be the
weird.
same.
That's just weird, yeah, look, yeah.
Yeah, that is weird.
Yeah.
See, so I wrote the
that's
negative,
weird,
and he's
yeah.
mad at me.
Fine.
Okay. Any other questions on that? Deacon, do you have the labs?
I have a printer, but on 7, we bought a new printer and it still doesn't work.
Okay, here's the inclined plane lab. I'll have to run off a copy of that.
You're talking about the purple sheet.
Yeah. Yes.
For the force weight on the front half of that, should that be the theoretical force weight or the actual?
No, the theoretical. Okay, now remember, these are two completely separate labs. Okay? Do not staple them together. These are two completely separate labs.
Right.
Now, let's talk about the inclined plane lab. So, on that one, there's two parts to it. First is the static friction. So here's the easiest way to visualize this. Here's the book. I lift it up. Why doesn't the block slide?
Force friction is greater than force parallel.
That's right, okay? You have a battle of two mafias. Right now, the frictional force is bigger than the gravity mafia. If I lift it up, at some point, what's it gonna start to do? Slide. So at that point where it just begins to slide, we set the force parallel equal to the force friction. You do the trig, tangent theta. One time you used trig identities outside of a math class. That was it. That was your shot. So on the first part, literally, all you have to show me is that you took the tangent of the angle. That's it. That's all you have to do. Now, the second one's more complicated. The second one, you're going to be dealing with constant velocity. So here's your 30-degree angle. Here's your block. When you pulled it up, Mr. Hanna, when you were pulling that block up the inclined plane, was that your applied force, your opposing force, or your force parallel?
Applied.
Yes. So that's your applied force. So on your diagram, I'm going to tell you straight up, here's the first thing I'm going to look for. That applied force is overcoming two forces, force parallel and force friction. So the first thing I'm going to do is look and see, is the applied force equal to the sum of those two forces? The first thing I'm going to look at, okay? So if your applied force is, say, 3 newtons, which is cool, that means these two values here, those two, if you're defining down as being negative, and I don't care, then those two values going down have to be like -1 and -2, okay? Some combination that's going to add up to 3, okay? The very first thing I'm going to look at. Now, that's 3 of the 4 forces, 3 of the 5 forces. What are the other 2 forces that are going to act on the system?
Normal and gravity.
Gravity acting straight down. And when you draw the normal force, do you draw the normal force straight up, or is it at an angle to the incline? Angle to the incline. It is not straight up. So I should be able to clearly see the scale. This better be drawn at an exact 30-degree angle. Maybe you let 1 centimeter equal Newton. I don't care what you did. Okay? Show me the scale. Now, let's talk about problems 1, 2, and 3. The common theme of all 1, 2, and 3 is that something is moving along an inclined plane at constant velocity. Okay, that's the common theme. So, on number 1, you've got the angle, you have the coefficient of friction. Your answer to number 1 should be in the low 20s. Okay? Somewhere in the low 20s. Now, the only difference between number 2 and number 1 is that you're still going to find the force it takes to pull it up. But again, this is where this problem meets the hanging sign lab. Let's say that you need 9.8 newtons of force. If you need 9.8 newtons of force to pull that thing up, Thatcher, what mass would you put on the end of the string?
4 kilograms.
How'd you get that?
Common sense. I don't know.
Well, does 9.8 newtons equal mass times your gravitational acceleration?
Yeah.
What's your gravitational acceleration? So if I take 9.8 newtons and divide that by 9.8 meters per second squared, I get,
1 kilogram.
there you go. That's how it makes sense. So, to get your answers to 2 and 3, find the force that you need, divide that by g, and there's your mass. So your answer to 2 and 3, those masses should be both of them should be somewhere between 0.1 and 0.5. Okay? So your answers to 2 and 3 are somewhere between 0.1 and 0.5. Okay. Any other questions? Please make sure that you do not staple both labs to each other. If you have diagrams, staple those to the back of one particular lab. Hand them in completely separately. Okay, these are going in as 2 completely separate labs in the grade book. Anything else? Once twice sold.
I'm going to